All right, here we go. Because y'all will probably want this. So here we go again. For this question, we said it's E, all of the above. Gases can expand. They have low density, which if you think about a gas versus a liquid like water, you can think about density in that way, and you can see that a gas is much lower density. And gases will mix completely. So you're not going to have a pocket of gas over here, that's more concentrated in nitrogen, and then another pocket that's got more oxygen. If you're talking about air, it's all going to be the same mixture everywhere. Does everybody understand that? Are we good? Okay. Alrighty. So this next one is a pressure conversion. Just like we were doing conversions in chapter 2 in the very beginning, you have to figure out your unit equation and your unit factor. Here we have the pressure of a gas is 15 millimeters of mercury. What is the pressure in atmospheres? So I'm curious, what did you guys get? Okay. So it looks like a lot of you got it. And I'll write it out just to make sure that everyone's on the right track, because I know everybody doesn't chime in. So what you should have done is take the 15 millimeters of mercury and use the unit factor 1 atmosphere over 760 millimeters of mercury. And that should give you, your calculator is going to tell you something like this. There's more decimals to it, I believe, but I'm not going to write all that out. And then with 2 sig figs, you should get 0.020 atmospheres. So good. I'm glad y'all got that. Which of the following would result in the pressure of a gas increasing? What's your answer? A, B, C, D, or E? Yeah. So increasing the temperature is going to result in increasing the pressure. So just to quickly go over the relationship, pressure and temperature, if you increase one, you increase the other. They have a direct relationship. For pressure and volume, is that an indirect or a direct relationship? If I increase the pressure, what happens to the volume? Does it increase or decrease? That's right, it decreases. So that's an indirect or an inversely proportional relationship. That's just pressure and temperature, and then pressure and volume. We also talked about volume and temperature. If I increase the volume, what happens to the temperature of the gas? And this is not related to this question. I'm just trying to go over the gas law stuff. Volume and temperature is the same thing as pressure and temperature. Yeah. It's a direct relationship. The only one that's different is pressure and volume. But pressure and temperature, volume and temperature are both direct. Whatever you do to the pressure or the volume, the same thing is going to happen to the temperature. I think this was one of the questions that someone wanted to go over. This is the nitrous oxide exerts a pressure of 100 torr in an 8-liter container. The volume of the container is decreased to 0.8 liters. What is the final pressure of the gas? What did everybody get on this one? That's what I got too. I'll go over how. When you're dealing with gas law problems and they're word problems, you have to pick apart what pieces of information you're given so you can figure out which gas law you need to use. Now, underline in the problem what we're given, and then we need to assign variables. So we have a sample of gas that exerts a pressure of 100 torr on an 8-liter container. Those are initial conditions. And we have a pressure and a volume. Our initial pressure is 100 torr, and our initial volume is 8 liters. The new volume, because it says the volume of the container is decreased, that's V2, okay? That's our second set of conditions. And that new volume is 0.8 liters. What is the final pressure of the gas? That's the question that we have to answer. We know that the units are going to have to be torr because that's what the pressure was in, the initial pressure. So we have pressure, volume, pressure, volume. What gas law do we use when it's pressure and volume that we're talking about? I know we didn't go over this, so it may not be super fluid. This is what the equation looks like. This is Boyle's law. So the first step in any of these problems is to identify the gas law that you need to use to solve it. From there, you figure out which variable you're trying to solve for. In this case, we're looking for P2. I always circle it so that I know what I'm solving for. And when you rearrange everything, P2 is equal to P1 times V1 over V2. Then you place all of your information in. 100 torr times 8 liters over 0.8 liters. And that should give you 1,000 torr. Questions about that? So the key here is identifying the right gas law. All right. We've got a couple more of these gas law questions, and then we'll get to some more of the more difficult math ones. The temperature and pressure have a direct relationship. When the temperature of the gas decreases, the pressure will, what's your answer? A, B, C, D, or E? Yeah. Direct relationship means that whatever the temperature does, which in this case it decreases, the pressure also has to decrease. So know those relationships. You will get questions like this on the exam. There's going to be a mixture of multiple choice, where, especially for the gas laws, where it's just a reasoning thing, and then you're going to have some where you have to do math and show your work. I think this is the final one for the gas laws. Which of the following scenarios would result in a decrease of gas pressure? What's your answer? A, B, C, D, or E? Yep, increasing the volume. So pressure and volume have an indirect relationship. We decrease the pressure, we have to increase the volume. So there's more space for those gas molecules to spread out, and they won't necessarily strike the walls of the container as frequently or with as much force because there's more volume. There's more space for them to run around. I always use toddlers as an example because that's my life. But if you take toddlers and put them in a huge backyard, they're not going to bump into each other as much. They still will, but not as much. If you put them in a very small room, however, they'll be bouncing off of the walls and the ceilings and the floors. So if that visual helps you remember the different relationships, feel free to use it. All right. Okay. So I put the limiting reactant question next because I figured that there would be questions on that. But we don't have to go here first. So I know that there were some requests earlier. So 5 and 10, 1 and 2, question 4. We did that one. 5, 1 and 2. So are you guys okay with doing the limiting reactant question? I know that the mole concept questions are coming up, and the empirical formula stuff, like the chapter 8 stuff, is coming up after this. So are we good with doing the limiting reactant question first? Okay. So just by a show of hands, how many of you had trouble with this question? Okay. Don't be shy. Okay. You can lower your hand. So if there's 3 hands, and I'm sure there's more that are being silent. So we'll make sure to go over this one in some good detail. So what mass of copper 2 nitrate is formed when 2.5 grams of copper metal and 2.5 grams of silver nitrate are combined? As part of your answer, state which reactant is the limiting reactant. Then we have this equation where solid copper is combined with silver nitrate to produce copper 2 nitrate and solid silver. So just as an aside, since we do have a final next week, this is an example of a single replacement reaction, where the copper is replacing the silver. And the question is asking how much of this product, the copper 2 nitrate, is formed when we have 2.5 grams of copper metal and 2.5 grams of the silver nitrate. All right. What kind of question is this? We had three different types of stoichiometry um, problems. What kind of problem is this one? Volume to volume, volume to mass, mass to mass, mass to mass. Yeah. So that's the first part, figuring out what type of question you have. Now, if you have your cheat sheet, which I hope you do, or you're working on it, you go to your cheat sheet and figure out how to solve a mass to mass problem. In general, what you're going to do is take your grams of given and you're going to use your molar mass that'll get you to moles of your given. Then you have to use a mole ratio, and that's going to get you to your moles of unknown. Then you use another molar mass, but this time with the grams on top. And it's the molar mass of your unknown. So that's what you should have, something like that on your problem solving cheat sheet. This is the generic mass to mass. So are there questions about that? The generic, how we get there? Especially those of you that have problems with this question, you gotta let me know, because I'm trying to pinpoint where the problems are. Alrighty. So I have another slide to deal with this too, and we can go back and forth as we need to. So the first part that we're going to do is figure out if we have 2.5 grams of copper metal, how much of the copper 2 nitrate are we going to make? We need some molar masses. What is the molar mass of copper solid? Even if you didn't do the problem, if you have a periodic table, you can tell me. Yeah, I wouldn't round it to 63 or 64. I would use for things like nitrogen and oxygen, they're so close to just that, to having no decimal places, it's okay. But with these others, you don't want to do that. So for copper, it's 63.546 grams per mole. You also needed to calculate the molar mass of the copper 2 nitrate. Do we have a molar mass for that? If you have your work from when you did it, it'd be helpful. No, that's not what I got. That's a bit low. Yeah, that's closer to what I got. I have 187.56 grams per mole. So let's go over that one. With a molar mass of copper 2 nitrate, it's going to be equal to the molar mass of copper, which we said was 63.546, plus we've got 2 nitrates, okay? So that's 2 nitrogen, which nitrogen is about 14. I'll put the 14.007 here. And then we have a total of 6 oxygens because there's 3 oxygen for every nitrate, and there are 2 nitrates. So we do 6 times, I'll just put 16 here. So you should get something in the ballpark of 187.56 or something like that. Yeah, you gotta multiply. No, it wouldn't be 6 for oxygen or for the nitrogen because there's no subscript here for the nitrogen. See? So you assume that the subscript is 1. That 3 is only for the oxygen. All right. Get rid of that. Now we're ready to start setting up the equation for, actually, let's do the molar mass of silver nitrate too while we're at it so that we have all of them. Take a second and do that if you don't have it. Let me know what you get. Yes. So as long as you get the 169 point something, you'll be okay. We'll all have the same periodic table for the exam. So if you still have questions about how to do molar mass, let me know in office hours because we can work on that. Now we've got to set up 2 equations. The first one is going to be figuring out how much product we'll make from the copper metal. We're starting with 2.5 grams of copper, and I'll do different colors so that you can see it. What's the first thing that we have to do with the 2.5 grams of copper? What's our first step? Molar mass of the given. Right. So we put 1 mole copper at the top. and we put the molar mass of copper at the bottom. Now we have moles of copper. What's next? We have to use a mole ratio. What is our mole ratio? We're trying to figure out how much copper to nitrate we make from a given amount of copper. If we go to the balanced equation, what am I putting at the top? Am I putting the copper to nitrate or the copper? Okay, Yao says copper on top. Anybody else have any votes? Ah, so we have two conflicting answers. We're trying to go from moles of copper to moles of copper to nitrate. So that means that we're going to need to put the copper to nitrate on top. If you think about it from trying to cancel out units, you have to put the copper on the bottom so that it cancels and you can get to the copper to nitrate. Does everybody understand that mole ratio? Because that's the thing that will really throw you off. Okay. So remember that it's always going to be the unknown over the given for these types of questions. Yes. So 1 mole is from the reactant side. So if you don't see a coefficient, fill in a 1. And what's the final step? Where we have moles of copper to nitrate. It's not the given. We already used that one. We have to use the unknown. Right. We have to do the molar mass of the unknown. Our unknown in this case is the copper to nitrate. So we're going to put that at the top. 187.56 grams. I'll never leave enough space. I don't know why I do that to myself. Okay. So that's how we set that one up. Yeah. Yeah. I can write that in too. So that's the copper. This is 2 times nitrogen and 6 times oxygen. Is that helpful? Okay. Because there's no subscript here for the nitrogen, okay? There's nothing there. So that means that it's a 1. So you multiply the subscript right after the element times what's on the outside of the parentheses. So you're doing 1 times 2 for nitrogen and 3 times 2 for oxygen. You're welcome. All right. So we set that one up. We're going to set up the same problem with the silver nitrate, and then we'll do the math. And I'll keep the colors the same too. So for the molar mass, Olga, you just want the molar mass of the substance. That the molar mass has nothing to do with the mole ratio. The mole ratio will tell you how many moles of substance you have, and you multiply the number of moles by the molar mass to get the grams. So just like before, you want to get to moles of silver nitrate, which is the other reactant. Then you have to do your mole ratio, which is going to be different because we're looking at silver nitrate and copper 2 nitrate. So what's our mole ratio going to be? What goes on top of the mole ratio? No, so remember, we're starting with silver nitrate this time. So we're trying to figure out how much copper 2 nitrate is made from 2.5 grams of silver nitrate. So it's still going to be the same thing on top because we're still trying to get to the moles of copper 2 nitrate. That's going to be the same. What's going to change is what we put on the bottom. For your mole ratio, you put your unknown over the given. Our unknown is still the same. The bottom, our given, is 2 moles of silver nitrate. Does everybody understand that? Make sure that you have on your cheat sheet for your mole ratio. Sure, I can go over it again. When you're doing these problems and you're trying to go from moles of one substance to another, you have to use a mole ratio that has the unknown over the given. If you identify your unknown, which in this problem is the copper 2 nitrate, that's what we're trying to get to. So when we first started doing these conversions, we said want over have. Now we're saying unknown over given. The unknown is what we want. We want moles of copper 2 nitrate. So that's going to go in the top. What has to go in the bottom is what we already have information for. We're already in moles of silver nitrate in this case. To get rid of the moles of silver nitrate so that we can convert to copper 2 nitrate, you have to put the moles of silver nitrate on the bottom so that they cancel. And you're left with the moles of what you want. Is that a little bit more clear? Good. The final step for this is going to look exactly the same. Because we're running a little bit shorter on time, I'm going to put the answers that I got. So from the copper metal, you would be able to make 15 grams of copper 2 nitrate. From the silver, you'd only be able to make 2.8 grams. So the silver nitrate is the limiting reactant, and you'd make 2.8 grams of your product. So you can go through that and try it again. Make sure that you get what I get. And if you still have questions, let me know. But what I want to draw your attention to is the two areas that are different. The molar mass, because we're using two different substances, and the mole ratio. Those two things are going to be different when you're doing a limiting reactant question. The last step, where you're converting the moles of unknown to grams of unknown, is the same. So you're going to have the same molar mass, and it's going to look exactly the same for that last part of the equation. But please, please, please remember the mole ratio. It's your unknown over your given. It's what you want over what you have. So we're going to move on to, I believe this was one of the questions that was requested. Yeah, number 1 and number 2. So I think Jaquan, I think you asked for this one. Whenever you see a question like this, the first thing you want to do is identify what type of problem you have. How many molecules of hydrogen gas are in 22.4 liters of hydrogen gas at STP? So what are we trying to do here? What is the question? If you rephrase it, what is the question? We're going from what to what? Not grams. We're going from a volume to molecules. Yeah. So we don't see anything about moles here. That means that we have to do two steps. The first step is going to be taking the volume of gas and figuring out how many moles of gas we have. The second step is going to be taking those moles and converting it to molecules. Yes. For volume to moles, what do we have to use? There's a term for the number that we have to use that we can convert volume to moles and moles to volume. Molar volume, that's right. Molar volume says 1 mole of gas is equal to 22.4 liters of gas. So that's our first unit equation that we're going to have to use to make a unit factor. If we're trying to go from moles to molecules, what number are we using? You can give me the name or you can give me the number. Yeah, exactly. With your powers combined, Avogadro's number, which is the 6.02 times 10 to the 23rd, and in this case, we'll say molecules, and that's equal to 1 mole. Now we can start setting up the problem. The math should not be hard. We've got 22 liters of hydrogen gas. We need to use this first unit equation, which is right here. 1 mole of gas is equal to 22.4 liters. If we're trying to go from liters to moles, what number should I put on top? The 1 mole of gas or 22.4 liters when we're setting up our equation down here? Right. We should be putting the 1 mole of, whoops, don't do that to me. We should be putting the 1 mole of hydrogen gas on top, which means 22.4 liters goes on the bottom. For our second unit factor, we're trying to go from moles to molecules. So where should I put Avogadro's number? In the top or the bottom? Top. You've been studying, girl. That's good. We put our molecules in the top and the 1 mole in the bottom. That cancels, and we've got 1 mole, so your answer should be 6.02 times 10 to the 23rd molecules of hydrogen gas. I still want to see the work for it, but you shouldn't have to touch a calculator for that problem. If you understand molar volume and Avogadro's number and the fact that they're all related to 1 mole, you can do this question without a calculator. Any questions about this? All right. If there's no questions, then I'm going to go ahead and do one of the empirical formula questions. So we're going to skip those for now. And I'm actually going to do this one, which is the more difficult one. I think there was a request for this as well. So are y'all good with doing this empirical molecular formula question? No. Good as in, is it all right if we do this one? Okay. All right. So mercurius chloride is a fungicide if the molar mass is 470 grams per mole and the percent composition is 85% mercury and 15% chlorine. What is the molecular formula of mercurius chloride? What you have to remember to get started is that the percent composition, you can represent it as grams and then figure out moles from there. So we're assuming that we have 100 grams of this substance. If we have 100 grams, then that means 85 grams of that will be mercury and 15 grams will be chlorine. And we can convert that to moles. So that's the first one. And the molar mass of mercury is just looking at the periodic table, see what the number says for the atomic mass, and represent it as grams per mole. We do the same thing for the chlorine. We're getting there. You jumped ahead. I know there was a request for this problem from somebody else. So we're gonna jump through it real quick. But you did it right. You did it right, yeah. So you get the moles of both, and you can see that they're pretty much the same, right? So 0.424, 0.423. So that means that the ratio of mercury to chlorine is 1:1. So your empirical formula is HgCl. Then you have to figure out the molar mass of your empirical formula. And that's just adding the mass of mercury plus the mass of the chlorine. And you should get about 236 grams per mole. There may be some, a few decimal places, but they're kind of insignificant. Then you take the molar mass of the molecular formula, divide, this is what they call the N, divide by the molar mass of the empirical formula, you get 1.99, which is pretty much 2. So your molecular formula is 2 times your empirical formula. The 470 came from the problem. We were told that the molar mass of mercurous chloride is 470 grams per mole. Yes. I just made it up. I just pulled it out of the air. I know sometimes it seems that way. So that's how you do that one. I think that we have time to do one more question. So we can either do another stoichiometry problem, or we can do a mole concept problem, like doing the grams to volume. I think that was a question that someone had. So put in the chat box whether you want to do a stoichiometry problem, or if you want to do a mole concept problem. Let me know what would be most helpful. And if you don't vote, then your voice will not be heard. We have a vote for the mole concept problem. 2 votes. Okay. Then let's do this one. There's 7.5 grams of ethane gas in a container. Calculate the volume of gas at STP. What kind of question is this? We're going from what to what? We're going from a mass to a volume, that's right. We don't see anything about moles on either side, so that tells us it has to be a 2-step problem. To get from mass to moles, what do we need? The moles will be on top. I'm looking for the name of what we need. Yeah, the molar mass. And when we write out that unit factor, we will have moles on top. On the bottom, we're going to have the number of grams in 1 mole of ethane gas. If you haven't, or if you don't have your paper, take a second and figure out what the molar mass of ethane is. You may hear my toddler in the background playing. It's his birthday today. He turns 3. So he's living his best life. Aw. He's living his best life. Thanks, y'all. I'm gonna miss y'all. I mean, past the class, I don't want to see you again in 103, but I'm gonna miss y'all. Get him? No, I make it. I make everything. I'm not gonna buy my baby a cake. I'm gonna make it. Yeah, I made the cakes yesterday. I got butter sitting on the counter to soften so I can make some buttercream icing. It's gonna be lit. It's gonna be beautiful. I just made a standard like yellow cake um, from scratch. Ain't no boxes. Ain't no boxes. It's gonna be a two-layer cake. There's a little bit of buttercream frosting in the middle, frosting on the outside. He likes yellow, so I'm gonna write happy birthday in yellow and then put some sprinkles and stuff on it. It's gonna be cute. We're not doing chemistry at all. Got me talking about my life on the YouTube video. Alright, let's get through this. So we're supposed to be doing molar mass. And the molar mass of ethane, I have it here, is 30.08 grams. So it's about 30. The second part, we said we're going to have to take those moles and convert to volume. We're going to make use of molar volume here. And we know 1 mole of gas has a volume of 22.4 liters at STP. We're going to put the moles in the top and the grams in the bottom, just like y'all said. And that'll get us to moles. Now we're trying to go from moles to liters. So what should go in the top? Yes. Y'all got this. When you do all that, you should get 5.59 liters of gas. And that's with 6 eggs. I will post when I post this, the annotated lecture notes, I'm going to finish doing all the problems out on these slides after class. And I will post it so that you have all of the answers so you can go back and look at them, not just the ones that we had time to go over. Are there any final questions that you have? It could be about the test, could be about the finals. So we ain't said nothing about dropping no exams, but I'm still going to drop your lowest 3 quiz grades. So I would recommend everyone take that. It's not an option, that's just what I do. So we've had the quizzes, in class, and then the assignments that y'all were doing and putting on Blackboard, that's also part of the quiz grade. So I will drop your lowest 3. Yes. So you can still, if you have not done some of the mini problem sets, you can still submit those up till the end of Thursday. So that's the last day of classes, April 30th. You can get all the work in that you can by that time. I'll take off 2 points for each assignment, but it's still, it will help you. Yeah, that's fine. If I emailed you and said, hey, you need to resubmit, and it's not going to be considered late. So your exam will be on Thursday at 11. It will be on Blackboard. We're not going to worry about respondus. What I want you to do, you're going to have to put your answer into Blackboard, or if it's a multiple choice question, you'll choose. You'll also need to upload your work. So make sure that when you're solving the problems with math, that you keep it neat and you write your name on it, and you're going to submit a picture of your work at the end. So that will be the last question for you to upload an image of your work. Um, if you need to submit more than one page, then what you'll have to do is take all your images, and then you'll have to use an app or something to make it all one document. So I know that ClearScanner will do that, and that's what I personally use with my phone. But I'm sure that there are other apps that will do that. Just make sure that you'll have the whole class period to do the exam. So 11 to 12:15. It's not going to be a long exam. The practice exam was probably a little long, but I wanted to make sure that there was enough practice of all the different question types. So you're not going to get, 3 limiting reactant questions, and I know that those take a little bit of time. Thanks, you too. If you don't have any more questions, we're done.